Okay, one more point to make about molecules and the structure of polyatomic ions is this idea of resonance. And this arises when one form of the molecule is more stable than another. And to do that, let's look back at that nitrate polyatomic ion, which we drew like this. Okay. All right, so we can see that each atom has a octet rule, but if we were to calculate the formal charge of each of the elements, again, valence electrons minus 1/2 bonding electrons minus non-bonding electrons, we would get values of 0 for oxygen, +1 for nitrogen, -1 for each of the other two oxygens. Okay, showing that this oxygen is sort of its most favorable point, 2 bonds and then 2 lone pairs of electrons. But why didn't we write this structure, the oxygen atom on the left with the double bond? Okay, that in turn would cause the oxygen on the left to have the 0 formal charge, nitrogen still +1, and the other two electrons or oxygens -1. Okay, so why didn't we write this? Well, it turns out that that makes a big difference for the individual oxygens. Overall, it's still a nitrate, -1 polyatomic ion. But it turns out that the switching between these two actually does occur in nature. To sort of make this as most stable as possible, this double bond actually rotates between the various oxygen atoms. And so we have one additional resonance structure, that's what these are referred to as, that we could write, and that's not right. With a double bond on the oxygen on the bottom. That would give this, the bottom one, the oxygen, the 0 formal charge. So what happens is that double bond, those 2 lone pairs of electrons, become delocalized and are shared across the entire structure, in this case, the entire structure, to achieve the lowest stability. So it turns out that all of these different scenarios occur at the same time. So really what we could write is a resonance structure as nitrogen with a dotted line in between the oxygen atoms and the nitrogen atom to indicate that that double bond goes back and forth between the various oxygen atoms. Okay, collectively known as resonance structures. Okay, ozone, O3, is another molecule that has a resonance structure. If we look at this, we can calculate that this ozone is 0 formal charge on this oxygen, +1, and then -1. So by this, that double bond becoming delocalized and switching positions, it forms the resonance structure shown here. Now, what do we know about this actual value? And it turns out that if we look at the bond length for various atoms, or for various bonds, it turns out that higher orders of bonds are shorter. Meaning that if we look at the carbon-carbon single bond, has a length of 154 picometers. Carbon double bond is shorter. Carbon triple bond is even shorter at 120 picometers. And that, of course, comes from the fact that there's more electrons in between those two nuclei. More electrons, more negative charge, stronger attraction pulls those atoms together. If we were to look at a nitrate polyatomic ion, its bond length is somewhere in between a single and a double bond, in that it is in resonance between those two. Same thing for that ozone molecule. It's shorter than a single bond and longer than a double bond in between lengths. Okay, finally, the last thing we want to talk about is exceptions to the octet rule. We already showed one with sulfate, polyatomic ion, having an expanded octet, and these do occur in various varying degrees in nature, and of course we'll come across them from time to time. And in general, we can have incomplete octets, atoms with less than 8 octets, not including, of course, the duet rule. That's quite common. This occurs for elements that are in between this very, very small ones like hydrogen and helium, and larger ones such as neon, such as boron. Boron happens to be somewhat stable with 6 valence electrons, although it is very reactive. You can also have odd electron species such as nitrogen monoxide. And nitrogen in this case has 7 valence electrons. These are called free radicals, and these are of course very reactive. Sulfur, again, can have expanded octets. So can arsenic. It's typical to see 10 and 12 valence electrons, as in those two examples. And what happens is, as we'll see when we talk about hybridization, the nearby D cells that are just slightly higher energy from the 3p or the 2p, or excuse me, the 3p orbitals, come down and sort of stabilize those extra electrons.